Hi everyone, I am Prexa Shah and I will be presenting my project on design and modeling of three-phase double-stage grid-connected solar inverter with MPPT system for the course ENGI 9863. The supervisor for this project is Dr. Mohsin Jamil. The overloading of grids due to wide energy use can lead to some serious problems like power blackout, power security, grid instability, and poor power quality. As a solution, renewable energy sources like photovoltaic source, wind, and biomass can be used to have a balanced relationship between energy generation and demand. Out of them, solar energy can be the most effective source because of its abundance, affordability, less pollutant nature, and less requirement of maintenance. To connect grid to the PV module, an inverter is used which converts DC power obtained from PV system to AC power. The voltage and frequency of inverter output and grid should be the similar. Therefore, in this project, I have designed and simulated three-phase double-stage grid-connected PV inverter with MPPT system in MATLAB. The different types of MPPT techniques are also discussed in the later part of the project. In this slide, the figure shows the block diagram of the proposed system. The system includes a PV module, a boost converter, an inverter with LCL filter, and the grid. The first component of the proposed system is PV module. It generates DC power from solar radiations and it can either be connected to the grid directly or by DC-DC converter. There is a semiconductor PN junction diode in a PV cell which helps to convert sunlight directly into electricity. When photons from sun strikes the PN junction diode, the electrons of the material absorbs energy and generates electron-hole pairs. After that, these pairs are separated by a potential wall, which in turn produces a voltage that drives a current through an external circuit. There are several ways to make a PV module, such as series connections, parallel connections, and series parallel connections. The output voltage of the solar cell is determined by the photocurrent, which depends upon the amount of solar radiations received during the process. The next component of the system is DC-DC converter. It is used to modify the output voltage from PV module and it is generally placed between the inverter and PV panel. Some examples of DC-DC converters include buck converter, boost converter, cuck converters or buck boost converters. To supply the right input voltage to the inverter, which also has the ability to stabilize and regulate DC voltage, the converter type can be chosen based on required size or capacity of the output voltage. In this project, a boost converter has been used. The third and important component of the proposed system is an inverter, which converts DC power into AC power. There are two types of inverter based on its supply quantity. One is voltage source inverter, which constantly gets voltage as an input, and the other is current source inverter with constant supply of current. In this project, a three-phase voltage source inverter has been used. An inverter contains two-leg power stage, DC link capacitor, and a DC input voltage source. It also has switching devices like IGBTs and MOSFETs, whose choice depends upon the system architectures, such as switching speed and power capacity. IGBTs are used for larger power capacities with medium switching speeds, while MOSFETs are used for lower power capacity and higher switching speeds. In this slide, the figure shows an actual simulation model of the proposed system. The upper half of the figure shows all the major components of the system like PV module, boost converter with PWM signals, an inverter with LCL filter and the grid. The lower half of the figure shows the control circuit of the system, which uses ABC to alpha beta and alpha beta to DQ transformation for easy control. This slide contains a table of specifications of the system. For solar panel, the open circuit voltage is 363 volts. The MPPT voltage range is 270 to 300 volts. The solar irradiance is 500 watt per meter square and the cell temperature of the solar panel is 25 degrees Celsius. For the boost converter, the switching frequency is 5 kHz, the inductance is 1.45 millihenry, The capacitance is 3227 microfarad and the output voltage of boost converter is 600 volts. The switching frequency of an inverter is 10 kHz and the inductance and capacitance of the LCL filter are 500 microhenry and 100 microfarad respectively. The line-to-line voltage of the grid is 400 volt RMS and the frequency of the grid is set to 60 Hz. In this work, the grid-connected solar inverter is designed to have a capacity of 50 kilowatts and to have the highest efficiency. Maximum power point tracking system has been employed in the design. The MATLAB simulating model of maximum power point tracking system is shown on the right side of the slide. The results of simulation of the grid-connected PV system can be seen in this slide. Figure 4 shows the output waveforms of the grid voltage and current. The figure is evident that both voltage and current are in phase with each other. The next figure shows DC output voltage from PV module which was recorded to be 600 volts. Furthermore, figure 6 contains power output of the whole system and the power recorded was 50 kilowatts which was desired power output. In the second part of the project, MPPT techniques are discussed and the best of them has been chosen for the simulation. The main purpose to use MPPT technique is to find maximum power point with minimum oscillations and fast tracking, to change the operating point to maximum power point in frequent climate variations, and to have the best efficiency of PV systems. Here is the list of various types of MPPT techniques. The first method is constant voltage method, which is the easiest method amongst all. In this type of MPPT technique, the voltage of PV array is changed to match it with the constant reference voltage while assuming negligible changes in insulation and temperature. The next method is short current pulse method. In this, a short current pulse of the PV module is used to identify an optimum operating current from where the maximum output can be received. This is a completely different approach as compared to the conventional methods. The another MPPT method is open voltage method in which the optimum voltage is kept somewhere near a constant percentage of open circuit voltage. To measure an open circuit voltage, a static switch is connected in series with PV array. The fourth method for MPPT is the temperature method. In this type, the open circuit voltage of PV array fluctuates with the changing temperature of the array while the short circuit current remains in direct proportion to the solar radiations. The perturb and observe method is the fifth in the list, which is also known as the PO method. It is the most effective technique for MPPT, and in this method, maximum power point is obtained by comparing the PV output power by perturbing the terminal voltage. The last method is the incremental conductance method, which is used to decide maximum power point where the equation given in the slide holds true. It works very good in rapidly changing atmospheric conditions. From the different MPPT techniques discussed earlier, PO method has chosen to be the best of them. The PO method is cheaper and it offers easy operation. It is known that at MPP, the ratio of change in power to change in voltage is 0. To track the maximum power point, the value of voltage can be calculated by equation Vn is equals to Vn minus 1 plus or minus m, where n and n minus 1 are current and previous moments, and m is lookup step. There is a flowchart of PO algorithm shown on the right side of the slide, which describes the whole process of the perturb and observe method. The PO algorithm is further divided into two types. One of them is variable step size method. It has variable step sizes due to which oscillation issues at maximum power point in a steady state condition has been observed. As a solution, two step size PO algorithm can be employed in which There is a larger step at first used for fast conversion to MPPT when the power difference is more, and there is another step which is smaller to eliminate oscillations. Using these modifications, one can improve the steady state and dynamic efficiency of the PV system. However, it does have some drawbacks such as the oscillation around maximum power point and slow speed at the time of rapid climate changes. The figure on the left shows grid-connected PV system with PO algorithm, and on the right side there is a graph showing power output of the same circuit. In conclusion, this project presents design and simulation of three-phase grid-connected PV inverter with MPPT system in MATLAB Simulink. The rating of the system is 50 kilowatt. The solar irradiance for PV module is 500 watt per meter square with cell temperature of 25 degrees Celsius. The system contains a boost converter, an inverter with LCL filter along with MPPT system to have the higher efficiency. The results of whole simulation are given in the slides above. Moreover, different MPPT methods are also discussed and best of them has been chosen, which is PO algorithm, and simulation of another PV system has been done with PO algorithm as MPPT technique. That was evident that more energy can be harnessed with PO algorithm MPPT system as compared to other methods. Thank you.